Okay, so good morning, everybody, and good afternoon to those of us who are not in South America. Welcome to our last seminar this semester and this year of our graduate program in climate sciences and also of our Department of Atmospheric and Climate Sciences at the Federal University of Rio Grande do Norte, UFRN. I would like to welcome you in our different format for this last seminar over Zoom, which was kindly provided by the Weizmann Institute. And with that, I would like to welcome our last invited speaker for this semester, Professor Ilan Koren from the Weizmann Institute of Science. Hello, Ilan.
Hey, hey. Good morning to everyone, and good afternoon to those who are from Europe. I see Hendrik. And yeah. Oh, how do we have someone from Turkey?
Yeah, Ilan, how are you?
Good, very good. How are you, Aki?
Thank you, Ilan. I'm looking forward to seeing you. Yeah.
Great, so we are very international today, so I'll be very welcome. Thank you for joining. And I will introduce Ilan. I don't know if you need to be introduced, Ilan, but I will just briefly say that you are an expert on clouds and the climate system, and will give us an insight to your work today. Ilan is a professor since many years at the Weizmann Institute and head of the Department for Earth Sciences, correct? And he did his postdoctoral work at NASA for many years, for 3 years, and before joining the Weizmann Institute. So, and your graduation and PhD were in geophysics.
True.
Correct?
Everything is true.
Good.
More or less, I mean, atmospheric sciences.
Oh, really? I thought it was geophysics.
It's the same. It's the same.
It's the same. Okay. Yeah, well, okay. Atmospheric science is part also of geophysics. That's right. Okay, good. So I will pass the word to you, Ilan, for your talk. And then you can speak for an hour. That's okay. We have time. And we also have time for discussions and questions and comments. We can, we have a very different, how do you say, audience, you know, we have people who are experts and people who are less experts. And so I think everybody will get a share from your talk today, right?
I hope.
So,
I truly hope. Okay, so first of all, thank you very much, Judith, for the invitation to give this nice seminar. And to me, I'm really excited because Brazil is like a second home for me. And I try to walk over Brazil or to be in Brazil as much as I can. And for example, I know many of the names that I see on my screen. So it's really a pleasure. Oh, and I see Laura from Chile. Yeah, and yeah, so I know many of the people here, and it's a great pleasure. I feel at home, but as you said, this is a very strange format, talking to the screen. So basically I'm sitting in my office and I'm talking to my screen, which, you know, usually I am not speaking with him. And I would be very happy if we could try to make this, talk as interactive as possible. So I know that there are Zoom limitations, but since my talk is very informal, I'm welcoming anyone who wants to ask, who wants to comment, who wants to clarify. whatever, please do. Otherwise, otherwise I will, I will see my screen and it's not fun. So with all the Zoom limitations, please feel free to interrupt and to ask. So Judith, you are the boss. Tell me how you want to do it. I mean, or let's try. Just try.
Yeah, well, I would just like to invite who wants to switch the camera on so that Ilan is not talking to a black screen.
Oh, yes, it's true.
I think that would be more pleasant probably for you. And yeah, look, there are a lot of people showing up. Look, there's Theo and Weber. And Hendrik. Oh, great. Elisa, everybody here. Good, great. So
okay, so now it
looks like
yes. So now it looks more like, oh, here is Alexandre. So now it looks more like Harry Potter chapter. So I see moving pictures. It's much more fun. And by all means, if you have comments, it's a very non-formal talk. You will see. I'm not going to speak on normal cloud physics, not at all, I promise. So if you have questions, comments, clarifications, please do. And I will start by sharing my screen. Now let me, do you see my full screen, my presentation?
Yes.
Good.
Okay. Ilan, just a small remark, especially to the students who are participating who may not be so used to using Zoom. When you click on the participants list, there is an option to raise your hand if you want to make a question. So there's a little hand sign, raise hands, and you can just click on it, and I will make sure that I see it, and Ilan too, and then you can just make a question. If you don't find this hand sign, just rudely interrupt and
yeah, exactly.
and make a question. Okay.
Let's start and see.
Yes.
So the title is New Approaches to the Cloud, Rain, Aerosol Climate System Challenges, which, when Judith asked me for a title, I didn't know what I'm going to talk about. So I said, okay, I will give the general title, the most general title that will allow me to improvise before the talk. So I don't think that it gets much more general than this title. Before talking to the point, I want to highlight members of my group that really you will see that many of the things that I'm referring to or showing or the ideas came during interactions with them or from their work. You will see few reference. So by all means, the stuff that I'm showing is not my work, it's mostly their work. And also I want to highlight two colleagues that you will see. I'm going to show you kind of a project that started as a hobby. It was so dangerous. I mean, I didn't want any of my students to deal with it because it was too new and too risky. So I played with friends and mostly with Graham and with Ellie. And many of the results, I mean, that you will see today are the outcome of this interaction. And now, again, as you are not supposed to do, I will list the topics that I will not discuss today. So, the title is a bit misleading. So I want to emphasize that I'm not going to talk about microphysics. Microphysics, as many of you may know, is a really great portion of my research and dynamics and microphysics. and cloud resolving models and observations, but not today. So I'm not going to talk about the very nice new approaches to cloud resolving models. And as you may know, currently, I mean, this week and next week is the AGU, and you can see many, many talks about super pixel, super Lagrangian approach, super parcel approaches. I'm not going to discuss these exciting ideas at all. This is not the topic of this talk. I'm not going to discuss new methods of observations or of how using measurements. So my work will be almost purely theoretical today. Again, not as most of my research. And again, to clarify, because of the title, it's not machine learning, AI approaches to cloud and climate. Not today. Again, very exciting, but not today. So once I clarify what I'm not going to talk about, I will move to the business, and I will start it with a quite traditional statement. So whoever is dealing with clouds and climate, and whoever needs to write a proposal, he most likely writes these lines, okay? That clouds play a critical role in the Earth's climate system. Clouds are responsible between 1/2 to 2/3 of the planetary albedo. So it's a big responsibility that clouds has on their shoulders, okay? A small error in our cloud measurements, cloud understanding could be translated to large portion of the anthropogenic effect in units of energy or flux, energy per time per unit area. So we need to understand theoretically clouds in a very high precision. Okay, and at the end, we always write that the inaccurate description of the cloud properties yields the largest errors in the climate prediction. In other words, clouds are responsible to great part, if not most, of our uncertainty in climate prediction. And I want to ask why. I mean, why clouds are responsible why clouds share such a large responsibility of our uncertainty? Okay, I mean, there are many complicated processes, nonlinear processes in the Earth system. It's not only clouds. We understand that dynamics has a lot of complexities, and we understand that the interaction between biology and the atmosphere is crazy. And again, fluctuation in the ocean and ocean dynamics and biology in the ocean, and you name it. And nevertheless, we say that clouds are responsible for most of the errors or most of the uncertainty. And the question is why? So first of all, I want to say that this statement is quite true to the best of my understanding, okay? I'm standing behind this statement, and I would like to focus the talk today on exactly on this question. Why? Okay, and in order to answer it, I want to take you to a question of errors, but we will not deal with errors. We will not deal with measurements problems, but this is the way to start. So if you have an inaccurate description of clouds, or of aerosols, or of frame, you can roughly classify the problem to more linear challenges and to more non-linear challenges. And nothing is linear, nothing is truly linear in our Earth system. Linearity is always kind of a nice approximation, but it works well for great regime of the physics. And you know, linear challenges could be error in the measurements. it could be even great chapters in radiation transfer. So if we have errors in the optical properties of clouds or the optical properties of aerosols, yes, it will yield an error, but the error will be proportional to the uncertainty, okay? On the other hand, if we are dealing with nonlinear challenges, it's very hard to estimate the error or the effect based on the perturbation. This is by definition a nonlinear system, right? That the link between perturbation and the outcomes is not easy to scale. Of course, once you have a subset that is nonlinear, even the linear challenges, if they are coupled to the nonlinear challenges, it all becomes nonlinear. And this is the case with clouds. And today we will focus the talk on nonlinear dynamics, nonlinear challenges. So we all like to say that cloud physics has a great of nonlinear portion, but I want really, okay, to look on the elephant in the room, to look on the eyes of the elephant in the room. Nonlinear challenges. And to dive in, because I'm sure that not everyone here is an expert in dealing with nonlinear dynamics, so I try to find an easy introduction to nonlinear dynamics, and this is what I found in Wikipedia, and it is very nice, but it's everything but simple. But anyway, you can see a brave guy that tried to take the field of complex systems and to classify complex systems, and you can see how wide nonlinear dynamics or complex systems are. So we can see the field of nonlinear dynamics, and you have the differential equations and the partial and the ordinary and the delayed equations in here. And you have the systems theory with the emergence and with feedbacks and how to do with feedbacks. And of course, pattern formation. Pattern formation is one of my great hobbies and challenges. And I will show you how we are dealing with it. And then we go to evolution and adaptation, but evolution and adaptation also refer to mathematical, non-biological systems and networking. So, you know, I will show later how network is all related, can be related to clouds. And basically, this classification is a good start, but actually it doesn't work because everything is everything. And you can take ideas from networks and put them on nonlinear dynamics, and you can take nonlinear dynamics and put them in system theory. And it's a brave attempt to classify this field, but actually, you know, it's very questionable. Two properties he decided to put out of the chart in the center. And actually, I like the idea. So the concept of emergence. Now, what is the concept of emergence? Suppose that we have a crazy system with hundreds of processes competing, and many of the processes are non-linear, and there are competition and feedbacks, and it's very hard, even with our best models, to resolve all the scales, all the problems that we need in order to solve the problem. We can take a larger zoom out and we can look for emergence. So what is emergence? Emergence is the outcome of all the competing feedbacks. So I can ask, can I find an island of sanity out of all these crazy processes that compete and try to take over? And if I do, I can use it. I can write equations that describe the emergent behavior, okay? And below you see self-organization. And this is very nice that he puts self-organization because it's common. This is common to all the fields that we see. and it is as important as emergence, okay? And I'm going to devote part of my talk today to self-organization. Good. So when, usually in traditional atmospheric physics and cloud physics, we are dealing, or we are not dealing directly with nonlinear dynamics. We see nonlinear dynamics, we have problems with turbulence, we have problems with mixing, we have problems with entrainment, but we try to resolve it as much as we can. We are not calling it all the time nonlinear dynamics, and by doing so, we are kind of strangers to the very exciting field of nonlinear dynamics, and I'm trying to combine the two fields, okay? So when people are talking about nonlinear processes in the atmosphere, what are the keywords that emerge or that come? So feedbacks, of course, we are dealing with feedbacks, we are worried about feedbacks, we want to know what would be the feedbacks of the climate system to global warming. This is #1 question, okay? Coupling, we know that processes are coupled, and that's what makes them very challenging and complicated. We have competition between processes. We have scale mixing. Scale mixing is an important concept. We cannot do easy scale separation. If we could, the answer would be much easier, but we cannot, because we have penetration, we have percolation between scales. Stuff that start in one scale propagate to the next scales, and so on and so forth. That's why, by the way, simple turbulence theory does not work well in cloud physics, because we have scale mixing and we have sources in many, many scales. So Kolmogorov approaches are very challenging when we are dealing with such a system. Bifurcation would be the hero of my talk, so I will explain more what are bifurcations and fixed points and attractors, and stability and non-stability, oscillations versus steady state, chaotic behavior, turbulence, dissipation, organization, and pattern formation. These are all keywords that comes when we study cloud physics and in general atmospheric physics or climate. And I want to really give them the respect in this talk. And now I want to translate, and this is going to be a long slide, and you are welcome to stop me, because I'm going to finish microphysics, everything on this slide. So it's like 1-2 minutes microphysics. So when we are talking about nonlinear processes, how does it reflect in cloud physics? So excuse me, all of these who are new to cloud physics, I will use terminology that is more on the expert level, but it would be only this slide. If we are talking about microphysics, we can start with the submicron scales, with nucleation of aerosols, right? We have primary and secondary aerosols, and we know that secondary aerosols nucleate, and we want to understand their nucleation, and it's not linear process, okay? We need to understand nucleation, and then I differ nucleation from activation of droplets, although it's very close. But when I say activation, I'm talking about activation of droplets as opposed to haze. And then we have the color theory, and whoever learned color theory, we know that it's completely non-linear. We have competition, we have feedbacks, we have bifurcation in the beautiful color theory. And then we have droplet mobility. Okay, once we created a cloud with droplets, it's very much important if the droplets are many and small, or few and large, because they will move differently in the cloud. On the next time step, they will be in different place within the cloud. So droplet mobility is you know, if you want to understand invigoration, you need to understand droplet mobility. It's as simple as is, but it's non-linear. It is linked to the activation. Okay, and then of course, we all know that collision coalescence of droplets and collection efficiency and rain formation is completely non-linear. We call it stochastic processes. Okay, and we know that we can look on two clouds and the clouds would be the same. They will look the same, they will have the same sizes, and one of them suddenly will start to rain and the other will not. And we want to understand this avalanche effect. Why? Why do we have such instabilities in the cloud? And then when we move up, we are moving to the crazy world of freezing and the three-phase problem and mixed phases and mobility of crystals and which, what is the shape of the ice crystals and so on. This is I finished my lecture on microphysics and I am moving to dynamics on the cloud scale. So once you understand microphysics, you understand it's tightly coupled to the dynamics. Actually, it's one field. You must understand dynamics in order to understand microphysics and vice versa. So we have coupling between microphysics and dynamics or thermodynamics, and we know that the supersaturation depends on the microphysics, of course. And the microphysics depends heavily on the supersaturation and on the buoyancy and on the updraft and on the latent heat release. So everything is coupled, okay? When we solve the differential equations, they are all coupled dynamics, microphysics, right? And then we have to partition the cloud to core and periphery. The core is more adiabatic, and therefore the physics is 100 times easier. However, on the periphery, we have mixing between the dry air. And how do we know if we have evaporation or condensation? Well, we don't. It depends, right? And sometimes you see a cloud, but actually it's evaporated, it's subsaturated. So you enter a cloud, it looks like a cloud, the buoyancy is negative, and the cloud is actually great part of the cloud is subsaturated. It takes time to evaporate. That's why we see a cloud, okay? And then we have coherent flow versus turbulence, okay? How come do we have inverse cascade in the cloud that small effects on the small scales percolate to create a coherent flow on the larger scales? Okay, it's very interesting. And we have, and now I'm going a bit out from the cloud, and we have the subsidizing shell of downdrafts around the cloud, okay? And then, of course, we have interaction with radiation. So again, order of magnitude more complexity because everything interacts with the long wave and with the short wave, and we must understand it. And then we move to the field scale, and we know that clouds change the thermodynamics that created them. So we must understand not only how the thermodynamics affect clouds, but how clouds affect thermodynamics. And then we have rain evaporation below clouds base that create cold pools and drives self-organization. And we have gravity waves, external and internal, and they all interact. So welcome to the nonlinear world of clouds, cloud physics, and it's a huge domain that you need a whole course or maybe 10 courses to cover. And actually many of the questions that I ask here are open, okay? They are not known. We try to understand them better, but they are not known. And today I will focus on small subsets. So I will focus on the larger scales, and I will focus on these keywords. So I'm talking about bifurcations, oscillations, steady state, and chaos solutions. And I'm going to give a lot of respect to organization and pattern formation. So you see, this is it's completely out of the standard regime of cloud physics, and I hope that you will find it important and interesting. So, bifurcations. Whoever is not familiar with the term, many of the functions that we are dealing with are nonlinear, and many of them have bifurcation. Bifurcation means that for a certain regime, they could be well behaved, and then suddenly, in a very sudden jump, they move to a different behavior. And whoever is familiar with the logistic equation, which is the most simple example for bifurcation, it's a beautiful example of how one of the most simple possible equations becomes crazy when we are exploring it in the parameter regime. And the stuff that you see in panel A it looks like the bifurcation period doubling of a logistic equation, but actually it's a cloud equation that I will introduce later. And basically you see for a certain regime that the clouds are well behaved, and suddenly they jump. Now, why bifurcations get such a respect in this talk? Because such a sudden changes can imply sudden changes in the climate properties of clouds. So we must be able to anticipate bifurcation, we must know how to calculate them, and we must know how to predict bifurcations. And I want to show you the simplest, most idea of bifurcation. It's not the best, but I'm relying on the assumptions that you are familiar with the water vapor feedback. So just suppose that we are facing a global warming. So global warming will be translated to increase in the SST, in the sea surface temperature. Actually, one of the most straightforward measures for global warming is changes in SST. So we will have warmer mixed layer, warmer ocean, and the ocean heat the atmosphere above it, right? So it's actually the long wave from the ocean that hits most of the atmosphere, and therefore we will have hotter atmosphere. So warmer ocean and hotter atmosphere above it means more capacity of water vapors and more evaporation. So we will have increase in evaporation. But as we know, water vapors are almost the best molecule for greenhouse effect, right? So immediately we have a positive feedback, right? Because the ocean is get warmer, the ocean evaporates more water vapors to the atmosphere that is getting warmer. So the capacity of holding water vapor is larger. We have more water vapor in the atmosphere. Therefore, we have more greenhouse effect. And therefore, we have more warming of the ocean. And it's a very disturbing positive feedback, right? And this positive feedback really fear us. I mean, we are frightening. We fear this feedback. Actually, it's a very central question that we ask. What is the water vapor feedback and how it will behave? But on the moment that we form a cloud, we reverse the effect. So at once, we move from warming to cooling. Why? Because clouds, by the phase change and by the droplet distribution, they reflect shortwave as opposed to water vapor and the rest of the atmosphere, or most of the atmosphere, right? So suddenly we have a reflector that reflect part of the solar energy back to space, and we move at once from a positive feedback to a possible negative feedback. And it is at once, because as you may know, clouds occupy, they use small portion of the water vapor in the atmosphere. So it's only tiny portion of the water vapor that have to become a cloud, has to reach a supersaturation, and boom, we have a transition from positive to possibly negative. Why do I say possibly? Because it depends if the system created cloud near the ocean or if it created high clouds, because as you may know, low clouds tend to cool because their shortwave effect is much more efficient than the long wave effect. They are too warm, as opposed to cirrus clouds or to anvils that are relatively optically thin and divisible, but they are very efficient greenhouse component. So this is the scenario that we want for negative feedback, and this is the scenario that we fear, that we will have more high clouds and less shallow clouds. But this was a very brief and not the most sophisticated example for possible bifurcation. And we will see many more actually later on in the talk. So we finished bifurcation, and now I want to talk about self-organization. So what is self-organization? Self-organization in a dynamical system means that first of all, you have interactions between the components, okay? If the components will not interact, will not be coupled, you cannot have self-organization. They need to transfer information. They need to affect each other. Now, self-organization could be due to very weak coupling. The coupling should not be very strong. Actually, there are many studies that shows that there is no weak coupling, okay? Weak coupling may take more to organize, but once you get organization, it actually can be very rich. So for example, we all know the V-shape of large birds migrating, and this is a very simple self-organization of these birds. And the rule is simple, okay? Each bird had to follow the birds either on the left or on the right. This is it. And by doing so, you get a V-shape, okay? And it's very easy to create, so the interaction, the coupling is very simple, and you see a beautiful V-shape or swirl or swarm shapes of birds migrating. And I want to say that you have self-organization all over nature. So of course, the upper left panel is clouds that we are going to talk, but the lower left is a canopy in the forest, and you can see how competition on the sunlight self-organize the canopy in hexagonal or almost hexagonal shape. And if we are talking about hexagonal, you can go and see the giraffe shape that is actually was proven to be statistically hexagonal. And we have the fairy cycles in the desert that are kind of, today we understand that they are self-organized, and I will be happy to talk more about them, but only if you will ask. So self-organization. I want to, usually when we talk about self-organization of clouds, we talk about marine stratocumulus over the ocean. It's beautiful, it's easy to see. But actually I want to talk today a little bit about my most beloved clouds, and most beloved clouds are over the Amazon, but not the monsters. I'm talking about the shallow, warm clouds that cover a great portion of the Amazon, especially in the early afternoon. Later on in the day, the convection takes over and it shifts to be deeper clouds, but you can see these clouds. Do you see the movement of my mouse? Can you follow it? You did? Can
yes.
you see? Okay, good. So these clouds are relatively small, and they are extremely sensitive. So first of all, they cover great parts of the Amazon almost throughout the year, not only on the dry season. You can see them on the transition season, and you can see them on the wet season. Of course, on the dry season, they capture much more area. And as you may know, smoke from biomass burning can kill them, and they are very sensitive. They are so sensitive and so spoiled that they are not willing to form over the Amazon. So actually you can see the Amazon by the absence of these clouds, okay? And let me zoom in. So this is Belém, and here you see the no cloud Amazon, and you see other streams of the Amazon, and it's beautiful. But if you will take zoom in, if you look on these clouds closer, you see that they are very well organized. So we have high level of organization. It's not a random organization cloud. So first of all, their size distribution is relatively narrow. You see that the size range is between few kilometers, between fraction of a kilometer to few kilometers. Actually, I could show you histograms later on, but not now. And if you can follow my cursor, you can see linear shape. So they tend to have linear shapes. And sometimes you see the linear shapes, and sometimes you don't see the linear shape, but it's between a grid to a linear shape. It's not random. And these clouds are really well organized. And what does it mean? It means that they have a way to affect each other. They are coupled. Otherwise, we will not have such organization, okay? And we are studying them, and now we published this year a paper showing that these clouds are actually very common under many different meteorological conditions. So you can find them in the tropics, of course, in the Amazon and in Africa and in Indonesia, and you name it, over the tropics. But you can find them also in the central plains of the US, and you can find them in Asia, and you can find them in Europe, in completely different environments. And you see how similar, you can see that basically from the snapshots, you cannot see great differences in the patterns, okay? The patterns and the size distribution are really similar. So clouds, many types of clouds, if not all of the clouds, are self-organized. And what is the difference between self-organized to organized to just organized? I will happy to answer or to discuss later. We are using to think about marine stratocumulus, which are shallow clouds, to be organized, but actually here we show deep post-frontal clouds, and these clouds are rainy and they are very large. I mean, we are talking about clouds of 6, 7, 8 kilometer thickness, okay? So it's not shallow boundary layer clouds, and I hope that you can see the cellular organization of the clouds, and these clouds form on the seashore of Israel. Okay, so this is the east part of the Mediterranean, and you can see transition from cloud streets to open cells, but these open cells are 6 kilometer clouds. It's not shallow marine stratocumulus. Nevertheless, we see a lot of similarities, okay? And below you can see the distribution of vertical velocities and rain, and you can see how rain can get kind of a train linear shape. And we are working on these clouds, and we see this cloud, this cellular shape are very common, and they are deep. And to show you how they form, I hope that you can see the movie. So this is a movie of one of the cases of the East Mediterranean, and the color refer to divergence and convergence. So,
Ilan,
yes.
sorry, it's a static figure.
Yes, I didn't start running it.
Oh, okay, sorry.
Okay, let's hope that it will work. The colors refer to convergence and divergence. Okay, so we have divergence if it's blue, and convergence if it's red, and the contours are contours of rain on the surface. Okay, and this is a real case that we try to model. And do you see the movie? Okay, and I hope that you can see the transition from cloud streets to cellular convection. You can see how slowly but surely the system is organized in cellular shape. And I hope that you are convinced, and this is a deep system. It's not boundary layer clouds of marine stratocumulus. We are talking about post-frontal, relatively deep system. So what's going on? Okay, we see kind of a general, universal way of organization of clouds. And I hope to convince you that it's very important to understand it. And now I'm moving to our beloved marine stratocumulus clouds. And these clouds covering great portion of the globe. And they are regarded as the reflector of the climate system. Why? Because on one hand, they are very shallow, so they are warm, so they don't have a significant greenhouse effect. On the other hand, they are very good reflectors, so they reflect a great portion of the shortwave radiation, the solar radiation, and it's really important to understand them. And these clouds come in two flavors. Okay, we have the vanilla and we have the chocolate. So the vanilla, we call them the closed cells, and they have very large cloud coverage, and their albedo is high. And the other state, we call it open state, and the open state is completely different. And basically we see great part of the ocean, and therefore the albedo is relatively low, and they reflect much less of the shortwave energy back to space. So it is extremely important for us to understand the transition between open to close. If we want to understand, if we want to calculate energy budgets. And we must understand how these transitions depend on aerosol and on the environmental conditions. So warmer ocean, what will be the translation of warmer ocean on such transitions? Okay, so I hope that you appreciate the importance. And in this picture, actually we see it's a summary of all of my talk, because we see, of course, self-organization. You see that the clouds are well organized and they have a beautiful patterns and beautiful shapes, but we see a very clear bifurcation, right? Because we have a sharp transition from open to close, and sometimes for the same environmental condition, okay? The same, completely the same thermodynamics, completely the same aerosol loading. So what is going on? Why do we have such a bifurcation? And not only bifurcation, we have a memory effect and we have hysteresis, you name it. It's so complex and so beautiful. So we see pattern formation, we see steady state, we see oscillations, and maybe we see chaos, chaotic solution, and I will show you why. In order to show you why, I'm zooming into one example. Okay, one example, how do I take all the bombastic words that I introduced so far and use them to learn something new. So I want to talk, to give you a short, brief introduction to open and closed cells. So suppose we see closed cells. So this is kind of a cross-section of the closed cells. And if we look on the internal dynamics of the closed cells, we see that the updraft is coming in the middle, and the downdraft is well confined and coming on the edges. So most of the cloud is updraft, but very weak updraft, and only on the walls we see downdrafts. Okay? And of course, clouds need updrafts to form, and therefore this is a very simplistic dynamical description of closed cell. This is the dynamics of each cell in the closed cell. However, in the open cell, it's the other way around. So the updrafts are along the walls, and the downdrafts are in the middle. So immediately you can understand that you will have clouds along the walls, and you have voids in the middle. So basically, it's kind of a topological problem. How to shift from closed to open? You need to reverse the dynamics. And there is a beautiful answer to this, but just I want you to appreciate that closed and open cells means different opposite dynamics. So this is closed cells, and this is open cells where the clouds form in the walls, and the center are voids. Okay, and now I want to design a toy model, and it would be so simplistic that it's almost a crime. Okay, so what are my basic assumptions? And please don't regard me as a criminal. My basic assumptions are, first of all, that clouds evolve, so I have enough instability to create a cloud, and the way that I describe the cloud is very simplistic. It's exponential function, which means that I have a kind of a saturation. H naught is the saturation, is the maximal thickness that the cloud would have, and it takes time for the cloud to build up, and it's kind of an exponential system. So I have the cloud shape depends on the time by which it takes to build up, and the scalar that describes the maximum thickness of the cloud once it forms. Okay, so this is one criminalistic assumption about cloud formation. The second assumption, and I hope that you will agree with me, is that rain consumes clouds. Okay, I hope that nobody is have a problem with this assumption. But, and here, this is the place where I cheat. So this line is very short, and this is the essence of my cheating for the last 5 years. There is a delay between the cloud evolution and the onset of rain and the consumption of the cloud. So it takes time for the stochastic processes to kick in and to consume the cloud. Okay? What is the delay? Well, the delay depends on aerosols and depends on the thermodynamics and you name it. But there is a delay. Okay? So the fourth assumption is aerosol affect all of the above. Okay, we know it. I mean, we learn microphysics and dynamics and invigoration and rain suppression and you name it. And we know that aerosol will affect all of the above. And we try to take these basic assumptions and to write equations that are based on cloud physics. So I'm not going to spend your time on the equations. My point is that all the ideas are coming from ideas from cloud physics. So nothing is imposed in from the outside. Okay, everything is coming from cloud physics. So liquid water pass is proportional to the mixing ratio, to liquid water content. And in a adiabatic cloud, liquid water content is growth linearly with height, and therefore we can integrate for the liquid water pass. And you know that marine stratocumulus are, I mean, the adiabatic assumption is not bad. But if the clouds are not adiabatic, the exponent here would not be 2, it would be a bit different. But basically, grosso modo, this is what we are doing, and we are saying that we have a kind of exponential term that let the clouds grow or recharge, and we have the discharge due to the rain, and the rain is proportional to the liquid water path, and the rain consumes liquid water path. So let me move on to the 2 equations that form our toy model. So basically, I mean, it's a crime how simple the model is, but I will talk about it a lot. It's a toy model. And for me, toy model is a compliment. It's not negative, it's a positive, because from toy model, there is a great chance that you will be able to learn something new. And later on, you will have to hook to reality to see if it makes sense. Anyway, so we have a differential equation for the cloud thickness, and we have differential equation for the concentration, for the aerosol, but it's not aerosol, it's CCN. It's the portion of the aerosol that participate as cloud condensation nuclei. And basically, it looks very, very innocent, right? I mean, it looks like OD, very innocent OD, but there is a cheating here, and the cheating is the delay. Okay, we have on the sync term, the nonlinear sync term, we have a delay. And once you introduce a delay to a differential equation, it is called DDE, delay differential equation. It is, you increase the complexity by many orders of magnitudes. And basically, many of the equations you cannot solve. Okay, you can explore, but you cannot solve. So we have these 2 cute equations that look innocent. And basically, I want to show you the results. Okay, I'm jumping to the results. So we run this toy model, and we held all the parameters of the equations constant, and we played only with n, only with the parameters that control the initial aerosol concentration. Okay, so we want to see sensitivity to aerosols. And what do we get? Okay, if we have very low concentration of aerosols, the system collapses. Okay, you cannot hold a cloud if you have no aerosols. Okay, clouds, as we all know, need aerosol, and if you have too few of aerosols, they will grow faster and they will fall, they will sediment, and basically it's an unstable system. Okay, you cannot hold a cloud in a very pristine, extremely pristine environment. And then when you increase the aerosol concentration, but still very pristine, you get oscillations. So when you solve the equations, you get oscillations. And I will explain later what are these oscillations. But basically, you get oscillation. But not only you get oscillations, the system wants to push the solution regime to the collapse mode. Why? Because once you get oscillations, you get clouds, there is a very strong, relatively strong rain, and then you have washout, and then from few tens of ccns per cc, you move to much less, and then the system again collapses. Okay, so the system wants to be locked on this mode. This is my point. Okay, so forcing, okay, let me go on. When you increase the aerosol levels, suddenly you suppress rain. And when you suppress rain, you close the cells, okay? And once you close the cells, okay, you get kind of a steady state. What is a steady state? Steady state means that you have drizzle, okay, but you have a perfect balance between recharge and discharge, okay? Recharge due to the thermodynamics of the cloud, okay? You always renew your cloud exactly on the same rate that the drizzle consumes the cloud. So this is a steady state, okay? And when you increase the aerosol concentration even more, basically it's a closed cells and you get kind of a saturation to the level where to the thickness of the cloud. They want to reach H naught. So basically, again, once we are locked on this regime, the system wants to stay in this regime, and basically we have what do we have? We have a classical bifurcation, okay? A classical bifurcation means that there is kind of a barrier between the two states, okay? And that once you are in one of the states, the system wants to stay there, okay? And you need kind of something, a forcing to push the system from one state to the other state, okay? So we have a bifurcation and we have these two possible solutions. Okay, now, as I introduced before, these two equations look so innocent, right? I mean, ODEs with the nonlinear term, but the delay makes them a monsters. Okay, so basically it's a monster to solve a problem. And we try even to simplify it, and we take a kind of non-dimensional form, and this is the form that we are dealing with. So we reduce the system only to one equation, it's unitless, and we did it non-dimensional, and look how innocent it is, right? You want to hug it. I mean, it doesn't get much simpler, right? But it's a monster, okay? And we are doing a lot of efforts to solve these nonlinear delay equations. And in two recent papers, we are showing attempts to understand this equation, and we learn that the system has bifurcation from steady state to oscillations, and then it moves to chaotic regime, and the chaotic regime is moved by period doubling. So you have more and more solutions as you move, and you have islands of sanity within this chaos. And then on a recent paper, we try to approximate this equation by ODEs, and we show that these ODEs can be approximated using the central manifold theory. And this approximation is not simple, but basically it allows us to investigate these equations in more standard tools. So far about this example. So basically, we took a set of equations that, it's almost a crime for how simple they are. And we learn that clouds could oscillate. We learn that we should regard closed cells as steady state. And we learn to estimate the bifurcation. And this is only from this toy model. Okay, so now we are developing a language for cloud physics, using nonlinear dynamics terms. Okay, steady state. Who is speaking about steady state and clouds, right? And who is speaking about oscillations in clouds? Well, on the recent, once we learn the solutions of these equations, we went back to many models that we run on cloud resolving models. And we could find in many different examples that actually, yes, we see oscillations. Now, the oscillations are not perfect and they are not clean, and it's always noisy. And of course, you have a lot of competitions and you change the thermodynamics and you name it. But nevertheless, if you take average properties of the domain, suddenly you see oscillations, okay? And this is for marine stratocumulus, but on a research work from 2 years ago, we took a cumulus, straight cumulus in the middle of the ocean field. And here you can see a temporal evolution of basically condensation versus evaporation of the whole field. And okay, you need some imagination, but I think that you can see oscillations. Good, so oscillations. Now, we wanted to find the link between closed and open and to prove it from data. So we took geostationary data and we developed ways. So let me do it a bit slower. These are 2 images of a satellite, of geosatellite, of the Severi instrument over the Atlantic. And I have here 2 examples of closed and open cells fields. And we developed a way to Lagrangian follow them. So basically, by using statistical properties of the field, we can follow the field throughout the day. Not using the advection, it's not a model. We use the data in order to follow it. And this is an example of correlation. And you can see that once you find the right displacement, it's very sharp. So basically, the quality of these Lagrangian followers were very good. And basically, we have kind of LES, but true data LES, because we have the same data following it for many hours, for the whole day. And basically, we took, let's focus on the open cells and on the closed cells. And basically, we followed the field for 10 hours throughout the daylight. And basically, we created a cross-section, a Hofmöller diagram of one of the cross-section. And what do I want to show? I want to show that, okay, so this is time of the day, and this is the spatial scale, and these are closed cells, and these are open cells. So basically, when you follow closed cells, you can see that they are in a close to be in steady state. Basically, you can follow the same cell for 10 hours. However, if you move to the open cells, you see them dance like crazy. You see the oscillations. So again, we have kind of a nice feedback that our primitive toy model could predict something real, or at least give us ideas about something real. And you know, we were very happy about the oscillations, but actually the steady state is even more interesting. Why? Because, you know, there is a very nice scaling law between the spatial size of a feature in the atmosphere and the lifetime of this feature. So for example, if you take a small cumulus, the lifetime of a small cumulus, or you know, order of 1 kilometer, would be half an hour, give and take. Okay, if you take a deep convective cell, a CB over the Amazon, it could be half a day to a day, right? And if you take a synoptic system, it's a scale of a week. So we know that there is a very nice link between the spatial scale and the temporal scale and the lifetime. And when we put the open cells, they sit really where they should be there, because the lifetime of a cloud in the open cell regimes is order of hours, okay? Because, you know, order of an hour. However, if you move to the closed cells that we call them steady state, they live much more than they should. So if you do analysis of the convective cell, you see that most of the cells in the closed cells are smaller than 10 kilometers. Okay, so it's order of 10 kilometers or less. Okay, so how come that a convective cell, that the size of it is order of 5 kilometers, can live 10 hours? This is really a strange question. And basically what we know is, the answer is that due to self-organization, these closed cells adopt the lifetime of the whole field. So basically you can imagine the whole field as lock in the state and very rigid. And basically it does not let the cell to fade away. It means that, you know, if these cells are living for 10 hours, it doesn't mean that the same water would be there for 10 hours. No, actually there is always circulation of the water, okay? It means that the recharge and the discharge of these cells are in balance. And I hope that this is clear. And my talk became very long, as always. So I will try to wrap up and to move fast to the next, to the last part. And the last part would be, okay, so we took a toy model and we described a very simplistic cloud that can oscillate or can be in a steady state, but how do you move it? How do you move forward? So in order to move forward, we need to couple between the clouds to create self-organization. So what is the way by which we should couple the clouds? Okay, so if you remember when we described the open cells, we said that along the walls there is an updraft, and the updraft creates a cloud, and the cloud grows, and once the cloud grows, it starts to rain. Oh, this is a game changer. Once rain fall below cloud field, we usually get rain evaporation. And rain evaporation is a very strong component that decouples the cloud from the feeding tube. So basically the feeding tube of fluxes that coming from the surface is decoupled by the downdraft that are created due to rain evaporation. And basically this could reverse the dynamics. On the other hand, when we look on the closed cells, on steady state, basically we have a convective cell that theoretically could live forever. Okay, so how do we translate such coupling to differential equations? Well, one way to do it, and this is an article that they did about our work in Physics Today, and I like their cartoon. So basically, they show exactly what we did, what we said today. That okay, at the beginning we have clouds and we have updrafts, and then the clouds start to rain, and the rain create downdrafts, and the downdraft encourage the formation of the next generation clouds, and kills the cloud themselves. So the next generation cloud will form, and later on will rain and create the next generation, and so on. So this is a very nice way to couple it, and we tried to couple it. So we created a way of coupling the clouds, and we added a coupling factor, so the clouds are affected by the state of their neighbors, and we created kind of Kuramoto springs, so we have many springs, and you can see the correlation between number of clouds. So these are the clouds that we had, and this is the correlation. And you see that some of the clouds are fully positively correlate and some are not correlate. And then you see complexity. Suddenly, when you move to a field regime and many clouds, all clouds affect all clouds, it becomes very messy. Okay, and we try to study it, and there are a lot of it. This takes us to network ideas, because we use Kuramoto network oscillators, and we try to study these clouds. I won't bother you with this. We saw a lot of complexity emerging in very simple question, and then we try to do it in a more robust way, and to actually take our simple equation and to add a coupling term. So the coupling term could be due to continuity. Basically, whatever goes up should go down, or diffusion. And I don't have time to talk deeply about this, because it's a cool stuff, but it's completely new. So I will show you first attempts of playing with such models. And basically, in this model, I put at the beginning only one cloud in the middle, and then all clouds are coupled. And you can see that the way by which we couple the cloud and the strength of the coupling really dedicate the patterns that we get. So sometimes the clouds prefer to maintain a circular symmetry. So the inner cycle is up, and then the next cycle is down, and then the next cycle is up and down. Okay, this is very regular. However, if we change the strength of the coupling, suddenly we get other solution. We get linear solution. We get very complicated solutions if we have interactions of other clouds and interactions with other processes. And then, you know, we can get regimes, very complicated regimes that start to mimic what we see on real clouds. And suddenly we see the coexistence, okay? We see clouds that oscillate, and near them, we see clouds that are in steady state. So suddenly we have coexistence, okay? And then we have something that, you know, this is more chaotic. So we can get chaotic solutions of this field. On the other hand, we get what is called POCs, a pocket of open self. And this is stuff that we see in nature, that basically we have a closed cell regime, but suddenly an area within the regime is open. And the question is why? And actually we see here that this could be a simple solution of the field, okay? Fluctuation, internal fluctuation of the field can create pocket of open cells. So you see, we took this as simple as possible model, and we can learn many things, okay? For example, here we impose the ship track. So we have a ship track area with the higher concentration of aerosol, and the question is, can the ship track decouple the lower part from the upper part? Okay, or is it still connected? Okay, and what the clouds could do to the ship track. And suddenly we can see that even within the ship track, we see oscillations. Okay, and I want to summarize my talk without giving many answers, but I hope that I introduce kind of an interesting approach to the problem, and I will return to my basic question. So the basic question is why clouds are responsible for the largest error in the climate prediction. And clouds are responsible because of the non-linear components, but now I want really to give it names, okay? So cloud system exhibit high level of self-organization, producing rich gallery of patterns, okay? The organization state, we call it sometimes phases, can bifurcate to other states, from closed to open, from cloud streets to trade cumulus, from feather to other. I mean, we have many different of states, okay? Some of the states are steady and some oscillate, and some show continuous evolution, which is more in the chaotic regime. Now, this is the summary, okay? Simple scaling laws will not apply for clouds. Why? Because without knowing what triggers these bifurcations, how they depend on the thermodynamic parameters and how to correctly capture them, climate models will likely to miss critically important player in the energy budget. So these bifurcations are key to our understanding. We must understand how cloud field jump from one regime to the other regime. We must understand non-linearities and all the attempts to find scaling laws to sub-voxel scales are very dangerous in the case of clouds because of all of these non-linearities. So my bottom line, my last line is that we must understand better these bifurcations. And thank you very much, and sorry for the long talk.
Thank you very much, Ilan. Amazing talk. Thank you. It was really very enlightening to learn more about cloud patterns. And we still have time, so it's not a problem that your talk took a bit longer. I think everybody was very interested and fascinated. So, but I will go on to the questions now. And actually, Theo asked a question some time ago, but I didn't see it in time, so I didn't interrupt you. He, I don't know if he wants to talk by himself or if
maybe, yeah, I mean.
Theo, please.
Hello.
Hey.
Hello.
Well, I was just wondering, you started your talk showing shallow cumulus in the Amazon, then you moved it to stratocumulus in ocean areas. I was just wondering whether it's possible to apply the same approach for shallow cumulus. It's a completely different dynamics, I know, but have you thought about this before?
Not only that I'm thinking about it, actually we have one paper in review and two more in boiling. We are preparing. So the answer is completely yes. Okay, and the answer is yes, because once you capture the way by which they're organized, the clouds are self-organized, it's you can start to formulate a toy model that is linked to the cloud physics, the best you know of these clouds. So of course, it would be challenging because fluxes from the Amazon are completely different to fluxes from the ocean, and we have a very strong diurnal cycle, and we have a lot of dependency, whether we are over the rainforest or over deforested area and so on. So yes, there are many challenges, but in essence, we use the same methodology now to study these clouds. So I hope that by the end, by the end of next year, we will have more concrete stuff to show.
Happy to hear that.
Mm.
Okay, and then we have a question here from Laura Gallardo, but she says she doesn't have a camera nor a mic, so I will just read her question. She says, Ilan, absolutely fascinating. A philosophical, but to some extent pragmatic question. Should we move to complex system theory? Our models are still highly linearized. Yeah, that's it.
Well. First of all, Thank you for the good words, and I hope that it wasn't too long. And I don't know the answer. So it's a very good question. I don't know. My privilege is that I am not a GCM person. So it's not fair. I complain about GCMs and I have a lot of criticism, but I never ran a GCM. And I know that it's a very challenging field, and people who are running GCM has to be so clever in so many fields. So I don't know if we can, the way by which I was thinking of adding the information is mostly by using better parameterization. So use whatever GCM you are using, but maybe you can add some clever functions that can capture bifurcations. Because if you want, you know, in a GCM pixel, you want to know the amount of cloud, the amount of liquid water content, the level of the clouds, the albedo. And of course, they are using a lot of assumptions, but I think that most of the assumptions will not capture bifurcations. Most of the assumptions are quite linear based. So I think that we need to find a creative way to translate such information to the GCMs. And I leave it to the GCMers to help us finding such a way.
Okay, thank you, Ilan. And now I will give the word to Alexandre Correa. We cannot hear you.
Okay, now you can hear me, right?
Now.
Yes.
Yes.
Okay, thanks, Ilan, for this excellent talk. It's amazing as always. Very good to see you and the people here.
Thank you.
I never wanted to hug a toy model, but I think I'm gonna start to think about that now. I would like just to know a little bit more about this, the first bifurcation you showed, like the D star parameter. You will start to increase it, and when it gets to 0.8, everything happens. That the magic happens there. So can you talk just about that bifurcation, because I think that's the first point that caught our attention here. So
okay, I want to share a slide. Wait. Wait. How do I? Oh, sure. No. Basic. Okay. Do you see my presentation?
Yes.
Yofi. So basically, to Alexandre, to answer your question, I want to find the best way to answer it. It's not simple question. It's not simple.
Don't worry.
It's not a simple question at all. So basically, when we use the normalized, the non-dimensional version of the toy model, we separated the variables to two components. So D would be the delay. Okay, do you see my mouse? Okay, so D would be the delay, and mu would be a fraction. Let's see if I can, I don't want to poison you with many equations. This is really not what I wanted. Okay, mu would be proportional to the aerosol concentration and to the thermodynamical parameters. So basically, when you increase when you increase the aerosol level, you increase mu, okay? When you make the cloud deeper, you decrease mu, okay? This is in a very simplistic way, but then this is the solution space. So if you draw, this is the parameter space. So this is D and this is mu. And you see that when mu is small, you are in the oscillating regime. Okay, so this is the oscillating regime. So one condition to be on the oscillating regime is to have a relatively low concentration of aerosols. And what do I mean by oscillating regime? Okay, so it's all competition of recharge and discharge. Okay, the beginning you have no cloud, and then the cloud grows exponentially. Once it grows exponentially, it starts to form rain. And the rain, it takes time for the collision coalescence and for the droplet collection to kick in. And this is the delay. Once the rain becomes efficient and goes and sediment below cloud base, it starts to deplete the cloud that created it. Okay? And then it depletes the cloud. It can deplete either all of the cloud, and then you're left with no clouds, or it depletes part of the cloud. Once rain stops, you have again recharge process. The cloud grows again, reach a stage, a critical stage, form a rain, and so on and so forth. So basically, we called it in the paper a predator-prey cycle, okay? Which the rain is the predator. So the bifurcation line in the parameter regime is this line, okay? This is the line that separates the oscillating part from the non-oscillating part. Now, with no delay, you will never have oscillations. You have only the steady state. So in cases of no delay, only steady state. Once delay kicks in, it depends on mu, whether you are in the oscillating or the non-oscillating. You can reach the oscillation, or you can reach the first bifurcation line or point, either by cleaning the aerosols or by making the cloud thicker. Okay, in a very simplistic, or you can play also with the characteristic time, but just this is the model. It's as simple as this.
Okay, thank you.
Sure.
Thank you, Ilan. Are there any more questions? We still have we have half an hour still. If there are questions or comments.
Yes, I have one question.
Hi.
It's Idikle has a question.
Yeah, Ilan, it's a pleasure to see you talking. I like the way you talk, because you have so many questions, and each question is a doctorate or a PhD. So I would like to know, since my research field it's air pollution, I would like to know the megacities in general emit a large amount of anthropogenic aerosols, mainly because of vehicles and industrial activities. So I would like to know how these anthropogenic aerosols contribute to the cloud formation and precipitation, because I'm really not sure if this kind of aerosols contribute to precipitation or not, or yeah. So this is my question.
It's a great question, and the answer is yes to everything. I mean, it depends. Okay, there is no one cloud. So it depends heavily on the aerosols that you emit. It depends heavily on the environment, on the local aerosols. And it depends on the thermodynamics, or on what type of cloud you are dealing with. So if you, for example, roughly speaking, if you, usually when we are talking about pollution, we are talking about fine mode aerosols. So the aerosols are relatively, I mean, sub-microns, right? And therefore they are not very good CCNs, but however, we have many of them. It means that the effect on small cloud, okay, small cloud, small warm cloud, is likely to suppress the rain, B, shorten the lifetime of the cloud significantly. Why? Because once you create clouds that is formed by many but small droplets, you increase the surface area. Now, the surface area means that you will have a very efficient condensation, but very efficient, the same way, evaporation. And due to mixing, because small cloud is mostly mixing, small cloud is mostly entrainment. You hardly have a core in a small cloud. So basically the mixing component would be more important and the cloud will evaporate faster. So A, you suppress rain, and B, probably the cloud will evaporate faster. However, once you move to a larger cloud, in which the ratio between core to periphery is larger, then it's a completely different story, because then you can kick in the effect of invigoration, and basically you change the mobility of the droplets. And so for the same updraft, the small droplets will move faster and up in the cloud, and then you increase the supersaturation, and when you increase the supersaturation, you increase latent heat release, and latent heat release increase the updraft, and you have many feedbacks. Okay, and then if you suppress early formation of rain, it doesn't mean that the overall effect would be less rain on the surface, because after a while, once you will get you get to the critical size of the droplets on the upper part of the cloud, collision coalescence or collection efficiency could be much better, because you have a higher concentration and you have larger contrast between the collector and the droplets. And therefore you can get both increase in the size of the cloud, increasing the lifetime, and increasing the overall amount of rain. So the bottom line, there is no easy answer, okay? Depends on if it's a marine cloud, it would be different from a continental cloud. And if it's a stratiform cloud, it would be completely different. And if it's tropical cloud, where the environment is relatively humid, again, it would be different. So unfortunately, there are no simple answers to such questions. The question is important, but the answer is super complicated.
Thanks a lot.
Thank you, Ilan. So now we have a question by Michael Cecchini.
Yes, hello, I'm Mikael. I'm a postdoc from University of São Paulo. And I wanted to ask a question about the shallow clouds in the Amazon specifically. I'd like to know what you think about what is the role of the cloud microphysics on this self-organization of the shallow cumulus fields. And because sometimes I get the feeling that we can reproduce these self-organizations if we have even with a simplistic microphysics scheme, for instance. Or do you think we need to have high precision in the microphysics description in order to study this self-organization and the cloud streets and so on?
So my first guess is that you can do with very simple microphysics. microphysics is very close to me, and we learned microphysics for many years and coupling to dynamics, but not here. So I think that you can keep it simple. Basically, these clouds are, they are hardly precipitating, right? I mean, you can find few events of precipitation, but the precipitation is not an important component of their formation. They are small, and you know, the environment could be polluted enough, so you don't see precipitation does not play a critical role in these clouds, and therefore, you know, if you use usually I am very suspicious in bulk microphysics, and I think that it can create a lot of problems. But in this case, if you want to learn cloud organization, I'm betting, okay, but it's not an educated answer, it's just my gut feeling, okay? I'm betting that you can, for a start, for sure, start with a very simple microphysics.
Interesting, because I think I was studying clouds in the Amazon during my PhD, and sometimes the microphysics feel like they are a response from the thermodynamics and aerosols, and they don't seem to affect it. It's hard to say because they are all coupled, but sometimes they're more a response from the thermodynamics and aerosols than they actually impact on the other way.
As I answer Erikle, I mean, it depends very much on which cloud you are dealing with. Okay, so if you go to the convective, to the deep convection, then I think that the Amazon is one of the best, if not the best, laboratory for cloud aerosol interaction, and many studies were done over the Amazon, and I was involved in few of them, and it's a beautiful place to show how important aerosols are. So if you go to deep convection, I have no doubt that you must know a lot about aerosols in order to understand the clouds. Okay, of course it is coupled, but this is a problem. This is why it's very hard to scale it to GCM, because the scaling laws, the simple scaling laws, will not apply to cloud aerosol interaction, because it's very, yes, whatever goes up should go down eventually. So you can do a closure systems, but what is the scale of the closure system? And where do you put your water vapor? And where do you evaporate the clouds? And how much of what portion do you rain and what portion do you evaporate? And aerosol play a key role in such questions. So when I said that for the shallow warm clouds, I would keep it simple, I would keep it simple as a first approximation. Later on, I will definitely add the more sophisticated microphysics in order to learn sensitivities. But at the beginning, just as a first approximation, I would do it. When you go to deeper clouds, for example, these shallow clouds, during the late afternoon, they tend to cluster and to form deeper clouds, right? And then it becomes deeper and deeper, and this cloud, the shallow dissipate. So if you want to learn such transitions, oh, you must know about aerosols, because the transitions would be affected significantly by aerosols. So as long as you learn the shallow clouds by themselves, okay, you have a discount, but be careful.
Thank you. Thanks a lot.
Okay, so the next question is by Raquel Albrecht.
Hey.
Hi, Ilan.
I don't see Raquel.
Hi, Ilan.
Here.
Ah, okay. Hi.
Ilan, I'm wondering that have you got
Yeah.
Yeah.
Sorry. It's Raquel Albrecht, and then it's you. Sorry.
Yeah.
Can you wait?
Yes, yes.
Okay, Raquel.
Oh,
Sorry.
that's fine. That's okay, no worries. So thank you, Ilan, for your excellent talk. And if you don't know me, I'm from University of São Paulo. Also, I work with Mikael, also in the Amazon. And some of your slides during your talk raised me like a few memories from watching convection over the Amazon along all these years. Is that you showed the example in the coast of Israel where you had the transition from the linear cells to the more deeper raining cells. And yeah, they are deeper, but then when we go to the Amazon, we have the same thing, but it is like the even more extremes. We go from the very small low-level boundary clouds where we can see those very nice street clouds that you also showed a nice picture from the satellites. And later in the day, we explode to the thunderstorms with the very cellular dependence.
Right.
And that raised me a memory of also that nowadays we have the geostationary lightning mapper. And we can see those features also on lightning, which will be actually on the transition, not from the low level, the very small ones, which we don't have lightning on those, but going from the ones with they're a little bit deeper and then the monsters. We can also see this transition. And so can we also call this like the bifurcations, or is just a matter of the diurnal cycle, or going to a more deeper question on the Mikael's line, where can we put the aerosols there on this timeline?
It's a great question. So great that most of the things I don't know. But it's very, some of the transitions could be less sharp, or could be due to a sharp transition in the environmental conditions. And we have to be careful. So for example, you can follow clouds and you can see, I'm not saying that this is the case in the Amazon, but for example, over Israel, over the Eastern Mediterranean, it's a frontal system. So many times you have collision between two body of airs with completely different properties. And then when you look from satellite, you see a very sharp change in the cloud properties. But over there, it's not a bifurcation. Bifurcation is something that is internal to the system. So basically, you leave most of the parameters the same, and you play only with one controlling parameter, and boom, you move from a stable condition to completely crazy condition. This is bifurcation. If you have a sharp transition, but it's due to external forces, then you need to understand the external forces. And in that note, you know, we have a strong diurnal cycle in the Amazon, so it's very challenging to decouple the effect of the internal dynamics from the effect of the diurnal cycle, from the effect of aerosols. And it's a beautiful question, and I have no answer, okay?
That's fine, that's why we are here, right?
Exactly, but it's a beautiful question.
Thanks.
Well, even so, it was a beautiful answer also. So now let's go over to Aki's question. Now it's your turn.
Hi.
Hi, Ilan.
Hi.
I'm wondering that have you got an experience or the papers related to the? There will be a good example to interaction between cloud and aerosol. It can be ship tracks, right?
Right.
And is there any evidence that during ship tracks there will be more convective clouds occurs or low level clouds? And during ship travels, the percentage occurrence of convective or low level clouds increase or decrease during the time? Have a trends?
Okay. I want to try and to show. Okay. Let me see. Actually, Aki, I think that you saw it on the summer school, but you will have to see it again now. Do you see my my screen?
Yes.
Okay. So to answer your question, this is a satellite, and I think that many of you saw it. So basically, these are few days, right? Or maybe one day over the North Pacific. I think that this is the west coast. You see the west coast of North America, and basically you see ship tracks. And I think that this can answer your question. So let's move to one snapshot. The so-called natural conditions are where I put my mouse. Do you see this corner of the slide? This is the so-called natural conditions. So you see that these are, I would not call them open cells because it's a mishmash between closed and open, but I will call them clouds with very low albedo. You see the ocean, you see that they reflect a smaller portion of the sunlight. And you see the sharp transition due to the ship tracks. So all the lines, all the white lines, white reflectance lines here are ship tracks. And basically, not only that we see ship tracks, even this part of the image, which looks completely natural, is actually an old ship track. So you can see the anthropogenic effect in a very clear way. It can close the cells or it can increase the albedo. And sometimes, not always, okay, it depends on the thermodynamics. Sometimes the ship tracks disappear fast and sometimes they do not form at all. But sometimes, if the conditions are relatively stable, they can last for many, many days. So here the anthropogenic effect of the ship tracks is huge. So potentially, I hope that I am answering your question, but I would not call it a bifurcation because it's not a delicate change in the aerosol concentration. It's a jump in the aerosol concentration from few tenths per cubic centimeter to few hundreds or maybe thousands per cc. So this is not a beautiful example for bifurcation because basically you increase the aerosol loading in few orders of magnitude. It's not this. When I say bifurcation, is small changes in the aerosol concentration and boom, the system jumps from one state to the other state. But if you want to convince someone that there is anthropogenic effect in the ship tracks, this is a very clear example.
Okay, so we can take one last question. Does anyone still have a question? At the moment, apparently not. So, Ilan, I will make some last curious question. to you. You said you had a lot to tell us. No, nothing complicated.
Now I am lost. Okay.
You said you had in the beginning that you had a lot to tell us about these fairy circles in the desert. And about it.
Okay. So you can consider me as Wikipedia, because this is the level of my understanding on the topic. But let me go. Okay, let me share the screen. Okay, do you see the slide?
Yes.
Okay, so these are fairy circles in Namibia. And basically what you see here is vegetation. Okay, so it's a natural shrub vegetation. And you see this area with no vegetation at all. And it was a mystery, because it is well known, and the locals, they have a lot of stories about the gods and how the gods created this fairy cycle. But it was from a natural perspective, it was a question mark. Nobody knows, actually, even until today, what is the best explanation for this fairy cycle. So at the beginning, the explanation was that it's a termite. So you have termites below it, that eat the grass, and what you see is a signature of the termites. Well, guess what? They went there and they couldn't find a single termite, or not enough termites. Okay, and then there were other ideas about, who knows, animals that are responsible for it, and they couldn't find the animal that's responsible for it. And basically, the current explanation is actually that this is a solution of the equation. So basically, when you solve the equations of the vegetation budget, and you have a limited amount of water, and you let the water, there is a competition of the roots on the water, you get such solution. So basically, this is a natural pattern that this is the newest explanation, okay? And they could show it in equations, that basically competition between evaporation and the percolation of the water and the roots spread dictate the formation of such fairies. So there is no external force, but it's all natural, and it comes from the dynamics, from the internal dynamics of the vegetation and the water and the atmospheric conditions. This is my Wikipedia level of understanding. Oh, and by the way, the scale is 10 meters. So these are large, okay, I think that you can see here a trail, and here you can see another trail. So it's very large. I mean, it's 10 meter scale. It's not tiny.
It's really impressive. I had seen it before and heard about the termites, but I didn't know about the dynamic solution.
Yeah, I mean, the termite was the common solution until people came there and looked for the termites. And apparently they couldn't find them.
Okay, Ilan, thank you. So we have no further questions here. And also it's almost 11 now, so we're coming to the end here. And yes, do you want to make some final remarks, Ilan?
I want to thank everyone, everybody here again for being patient and for sitting in front of the Zoom for 2 hours. It's challenging. I know, I have a Zoom fatigue after 15 minutes. So thank you very much for staying. and it's a great pleasure to see so many friends.
Okay, so people are thanking you here in the chat and thanking you for your great presentation. Yes, Ilan, I also want to thank you for accepting our invitation of our graduate program in our department at the Federal University of Rio Grande do Norte in Natal, Brazil. And also especially thank you to that you hosted your own talk, actually.
Oh, right.
Weizmann Zoom system, because ours was booked, fully booked by other colleagues and other events.
My
so
pleasure.
very much
On behalf of Weizmann.
Yes, it was really the best solution. Thank you very much. And I thank everybody for joining us today. It was really great to have you all here, all the cloud-aerosol-climate system competence here, and students and postdocs and professors and researchers. So and other guests. So I thank you all very, very much. And yeah, it's the final seminar of our seminar series this semester, which all happened online. And we have all the talks also on our YouTube channel. And Ilan's talk is the only one that was not transmitted live, but we have it recorded, and I will make sure that it will be available on our YouTube channel. It's the YouTube channel of our center. So it's the Center for Exact and Geosciences at the university, and a YouTube channel if you want to send it, the link to someone who you think would like to see Ilan's talk is this from CCET UFRI, and I will write it here. So just, you know, if you look for it in YouTube, you will find the channel of our center, CCT UFRN, and I think until tomorrow, so Ilan's talk will be there. And we also had many different speakers, and one other talk in English, actually by Laura Gallardo, who's also assisting here, was. And the other talks are in Portuguese, however. But for those of you who speak Portuguese, there are many more of our seminar cycle. So thank you very much for joining, and I wish you all, yes, Merry Christmas already, because it's our last seminar talk, and a Happy New Year 2021 with a lot of vaccines and less pandemic, and with a lot of, with a lot less restrictions than we had this year. So all of you take care, and Ilan, thank you very much again, and hope to see you soon. Bye-bye.
Thank you, Ilan. Thank you, Judith. Thank you, everybody.
Thank you. Bye-bye.
Bye-bye.